Uh, Thanks for having me here today. I'm here to basically start what I'm calling the plastic conversation. We've arrived surreptitiously in the plastic age without a lot of fanfare and a lot of associated understanding of the compound that defines our age. We've outstripped the production of steel with our plastic production. The current plastic production is such that the weight of every man, woman, and child on Earth is equaled by our plastic production every 2 years. And yet, it's very difficult to find information. Schools are not teaching polymer science, although the world's chemists are principally polymer chemists these days. That's a specialty, and we're wearing it. Our food is delivered in it. We're driving in it. It permeates our lives. And yet we don't have the tools to make decisions about where it belongs. It doesn't belong everywhere. It's everywhere now, and there's some unforeseen consequences that lead me to believe that this is not working, that all plastics don't belong everywhere, and we can't continue to freely permeate the biosphere with every conceivable type of plastic polymer. So we're going to get into that discovery that I made, and the issue of plastic polymers with this lecture. First of all, I did not discover the North Pacific gyre. My work was in the eastern North Pacific and looking at a particular phenomenon, the accumulation in this gyre of our civilization's detritus. But the gyre was well known to biologists at the California Department of Fish and Game in 1960 when they made this pamphlet on the migration of albacore. That's where I got this diagram. This is the North Pacific subtropical gyre, okay? And I like it because the arrows kind of indicate there would be a recirculation pattern in this area, and there would be another one over here, which actually is the fact. Now, our government, National Oceanographic and Atmospheric Administration in the United States, has created this diagram, which shows that the convergent zone where debris accumulates is just below the transition between the low pressure systems up in the Gulf of Alaska and the Bering Sea. And let's go back there. And the Bering Sea here, these are low pressure systems. And counterclockwise rotating currents, they spit out debris, and the clockwise rotating currents accumulate debris, and it converges along this here. It doesn't mean that these other areas are free from debris, it just means that there's a higher concentration of it here. Now let's talk a little bit about the causative forces that create this convergent zone. And you can see them here in the averaged 3-month pressure, surface pressure over the North Pacific Ocean done by James Ingram Jr. His life's work at NOAA was to model the surface currents so that they could determine where fish larvae would be likely to go so they could protect the areas for important commercial fish species. Side effect of that is that we get to see the creation here of the gyre. Now, air heated at the equator rises, okay? We know this, hot air rises. It's replaced with cool air moving in, which has the effect of pushing these air masses north and south of the equator. And as the hot air that has risen moves toward the pole, it creates this mountain over the mid-latitudes, and that's what this H is here. The H that you see kind of moving around, but having a locus of points near halfway between San Francisco and Hawaii, that mountain of air is actually a high pressure system. That's what the weatherman means when he says high pressure. It's the weight of this mountain of air is higher. It's a heavier weight of air pushing down, and as it descends, it moves in a clockwise direction. That force is the force that's creating this gyre that's moving around, sweeping the Pacific Rim and bringing that debris into the convergent zone. Now, I've been out to this eastern part of the North Pacific numerous times doing research. And this is the vessel that was described, built in Hobart, Tasmania, launched in 1995, an aluminum-hulled catamaran. It is actually purpose designed to be a research vessel. It's also purpose designed to fit in my dock where I live, which is underneath this 12-foot bridge. So that mast, every time I come home, has to go down, and the boom comes down, and it lays flat, and that big, tall sailing vessel becomes 12 feet tall and goes under the bridge. But once the mast is raised back up, it's stable, and we can climb up and have a good look around, and we launch these manta trawls. Now, this is the instrument that we use to survey the surface of the ocean. The surface layer of the ocean is known to oceanographers as the neuston. The neuston layer is the layer that we study. It's not very deep. It's a shallow surface layer, and we sample it with this device, which is called a manta because it has wings like a manta ray and a wide mouth, and it trails this 1/3 of a millimeter mesh net out behind and has a collection bag at the end that gives us the sample of what is living or existing in the neuston. This is my body of work. Every time that I've deployed that manta trawl out in the North Pacific is one of these dots, and different research voyages that I gave in that previous slide for the different years are indicated by different colors. And the farthest west that we've been is the international dateline. 180-degree meridian of longitude is the international dateline. That's where you lose a day or gain a day, depending on which way you're going. So we kind of had fun going back and forth, you know, looking on the GPS, being yesterday to tomorrow, you know, going back and forth like that when we're out there on the dateline. But the major study area we studied in 1999 is that kind of inverted V right here, where you see several layers of dots on there. That we've sampled 3 different times and seen a remarkable increase. And it was said that the ratio of plastic fragments to zooplankton in 1999 by weight was 6-to-1. If you average the 2008 study, which was wintertime, and the 2009 study, which was in the summer, we wanted to see if there was much difference there. Now, 10 years on, that ratio has gone from 6 kilos of plastic for every kilo of zooplankton to 36 kilos of plastic to every kilo of zooplankton. So when we depict that so-called garbage patch with a extrapolation of our data and give a brighter red color to the area of higher concentration, this unscientific concept that the garbage patch is twice the size of Texas begins to take on at least some kind of a meaning. No scientist would ever choose Texas as a unit of measurement, but this is a fairly accurate depiction of the area where the greatest concentration of plastic is. You can kind of see the, you know, where Texas is. It's a big state. You could put maybe 2 of them in the area where that map is blushing the brightest red color. So it's not a totally meaningless concept. This map will be elaborated, you know, and refined with further study, but that's what we've got so far, modeled plastics density. Consequence of having all that plastic out there is more than simply a number on a piece of paper. This is a new habitat. This habitat now is producing growth on these persistent plastics. They assume the character of rocks or coral heads out in the ocean and begin attracting fish which normally would be found in an atoll or island habitat, so that we have a myriad tropical fish species living out there, and things like caulking tubes that you'd use to caulk around your bathtub. This is an invertebrate here. I think a giant polychaete. We've been finding huge polychaetes growing out in there. The Hawaiian sargent is a tropical reef fish. The scrawled or scribbled filefish is described in field guides for divers and ichthyologists as a tropical reef species found in depths to 120 meters. Well, I found this in 3,000 meters of water. Why? Because the habitat suitable for this fish's survival now exists in the middle of the ocean. The frogfish is a chameleon of the reef. It can change colors. Here are two frogfish that we captured out in the gyre that are the same species, but one was colored to match, say, a black fishing buoy, whereas the other one was maybe modeled to match bright-colored fishing line and nets. And these are lion-weight predators. That's why they have this ability to change colors. They hide camouflaged by some background item and then dart out when a prey species passes so that they can gobble it up and eat it. Well, in the deep ocean, the color is blue. Way you camouflage yourself in the deep ocean is you look silvery on the bottom. So if you're looking up, you see the silver on the bottom of that mahi-mahi blending into the sparkling surface water. And if you look down, like you see the back of this mahi-mahi, you see the dark blue color on the back of the fish looking down into the deep blue and is camouflaged in that manner. That's the typical camouflage for fish in the deep ocean. Not this ability to be chameleons and change to all kinds of different colors. But because there's so much debris out there now, you get these fish like the frogfish associating with that debris. Now there are pelagic species that do associate with debris, that are known to associate with debris, like this oceanic triggerfish, and they have really strong kind of beak-like jaws that can do what you see there to that soap bottle. I've got examples on the table here of bottles that are chewed up. This is one of the Comet Cleanser that's completely eaten away. Nothing left but the top on it. That ability is part of why they like the debris. It's not only food for them and produces growth which they can consume, it's also shelter, a sanctuary, a habitat for them. It's as if it was, a pocket in a coral reef or something. And you've got tanning salon. I mean, this fish is not sick. That's not usually when you see a fish looking like that, you go, oh, this fish is in trouble. But that's not the case here. What's happening is this fish is completely relaxed. It doesn't look like food to a predator. It's viewed from underneath. It doesn't have a natural shape, so it doesn't appear like something that a predator would go after. So it can stay there for days, just kicked back. Extremely lazy situation. So we find this all the time. Fish involved in this new habitat, completely relaxed and not afraid. And when you approach them, it's not like they leave the sanctuary to swim out. It's the total opposite reaction. They just go deeper into the object, and by that triggerfish chewing holes in a soap bottle like this, it makes a habitat for the vegetarian fish like these rudder fish that are oceanic vegetarians. They can hide inside there, so they hang around. Small pieces of trash always have fish hanging around them. They're fish attracting devices. We've actually found bottles like this where the fish has grown to maturity inside and can't get out. We've had to cut open the necks of oil cans to get the fish out. This is a Ziploc baggie. Just about any kind of plastic has the texture of natural food. There are cellulosic compounds in jellyfish-like creatures out in the ocean that nature has evolved mechanisms to eat, so that it's not as if this baggie appears as something, so foreign that nothing would eat it. It's like it makes sense that this would be something food-like, and it's obvious here that it's being sampled by a lot of different creatures. So Dr. Hank Carson at the University of Hawaii Hilo has the first mandate to investigate these kind of issues as the first and only postdoc who has been hired specifically to investigate problems associated with marine debris and plastic trash in the ocean. Our foundation helped fund his position, and he's now gotten bite samples out of museums and paired them up with bite marks that he's found on oceanic trash and prepared this graph of bite mark distribution by size. On the left are carnivorous teleos, meaning meat-eating bony fish. Chondrichthyes are the sharks and rays, herbivorous bony fish, and then the reptiles being your turtles with the larger bite marks, obviously, and then the birds down there with the fishes in terms of the size of the bite mark. And a fairly high percentage, as you can see, of just the trash that we find has got these bite marks on it. And this is stuff he's picked up on the beach. I'd say stuff that we pick up out of the ocean, the percentage is even higher. Plastic trash bag is habitat out in the ocean. Crate is an apartment complex. This is probably cooking oil. The cook from a fishing boat used the last jug of cooking oil and tossed the crate over. Now you've got the cafeteria, you've got the apartments, you've got everything you need there. This is growing. These are vegetarians. They're perfectly capable of consuming these algae and sea urchins and incipient barnacles growing on the sides here. Is just that's how we're able to find fish inside of oil cans that have grown to maturity inside. You think, how would there be enough food to grow a fish to maturity trapped inside an oil can? But it actually, the proof is there by finding the fish that's healthy inside an oil can. There's enough food to grow a fish to maturity inside an oil can to where it can't get out. One is tempted to say that it's traded freedom for security, but that's nothing that I know that we would ever consider doing. Here's a barrel of fish. We find a lot of 50-gallon drums out there, and the same thing. You bring it up on deck, you'd think, well, the fish would have long gone by there. No, just dump it out, and you get a barrel full of fish on deck after you pull a barrel out of the ocean. This is a Canadian Navy photo. Their vessel was transiting from here to Japan, and they were tangled by this derelict fishing net, and they sent me an email saying, we understand that you're studying marine debris. Could you please tell us where all these nets are so we can not get stuck in another one? And actually, it sounds like a ridiculous question, but actually the government has spent a lot of time in the United States trying to find out where they are, because they spend millions of dollars every year removing an average of 52 tons of these derelict fishing nets from the pristine Coral Reef National Monument declared by President Bush just a couple of years ago, stretching from Kauai all the way to Kure Atoll north of Midway Island. So it's a huge, long national monument, has a lot of focus on it now since it's been declared a national monument, and a lot of money and energy. And, a diver in tiger shark infested waters has to carefully try and struggle to remove and not break off these sensitive coral heads, these giant nets, it makes a lot more sense, rather than wait till they have destroyed coral like a bowling ball in a huge wave being dragged across these reefs, to catch them before they would hit the coral reef habitat. So they've spent a lot of money and got a lot of science looking at how to determine where these big blobs of net will hang out. So I actually had read that paper by Pichel, and this is the diagram they came up with. They used wind stress, curl, sea surface temperature, salinity, and came up with a what they call a debris estimated likelihood index. And then to prove that, they did 3 overflights. That's what the different colored towers are on this graph. And those 3 overflights identified this locus of points in the spring, March and April, where those nets are likely to be. So I forwarded that paper to the Canadian Navy, and I hope, maybe if they avoided that area, they may have had fewer encounters with debris. But personally, I had an encounter with it outside of that zone. There's no guarantee that you're not going to hit this stuff. My vessel stopped dead in the middle of the night. An engine was completely disabled by having this net wrapped around its propeller, and I had to dive over and cut it off. So there's other consequences to us besides what I've described about the change in the habitat. But when I say that the habitat has changed, I'm not speaking, figuratively when I say it's a coral reef habitat. It's literally a coral reef habitat. There is the coral. The coral is growing on plastic trash in the ocean. It's growing quite frequently. We're finding more and more stuff. This is a day's catch out in the gyre. And where we seek to net this stuff up, we stand on the bow, we point, the helmsman drives over to where we think we see something, we net it up. Sometimes we back up to it and get it off the swim step in the back. This is an afternoon's netting along Langmuir windrow. Langmuir windrow, when the wind blows over the surface of the ocean, it creates these cells that rotate, and the cylindrical Langmuir cell creates the counter rotation in the next adjoining cell, and you get this dredging effect where it pulls up debris and leaves a line of debris on the surface. You've all seen it in the foam lines that you may see when you visit the ocean, or lines of calm you'll see in a ripply surface on the ocean. Let's say when you're on the ferry or something, all of a sudden you'll see like this line of calm water and wonder why there's a river of calm out in the middle of the ocean. It's these 2 Langmuir cells that have created this phenomenon, and that's where we look for trash. And this particular batch of trash happens to have a basket which was used for sorting fish on a fishing boat, and here's coral growing right there. So this is great habitat. This has got like a place to hide in this corner of this basket. It's got coral growing, it's got algae growing, it's got all the ingredients for a new pelagic coral reef habitat, a new phenomenon. So the kind of research I want to start doing, and I think in 2014, 15 years after my discovery of this garbage patch, at least the first time I sampled it was 1999, bring scientists out there that are experts in coastal ecology and get them to characterize how this new coastal type habitat, what is it that we're building out here with our garbage? This is the most common type of float that we find out there. It's a 300 millimeter black float. You can see it there with the other kinds of debris that we haul up while we're out in this garbage patch. And I also find the most common type of glass float is these large green floats. Over many years, over a decade of sampling out there, I've just come to recognize these as the most common kind of glass one, most common kind of black one floating around out there. And I assumed it was from some fishery. I didn't really know, and that's one of the problems we have is this forensics, trying to get back to who's creating this mess out there. And it was revelatory in last year when a Korean broadcasting corporation contacted me about doing a documentary on this issue. I agreed to be one of the segments in the documentary, and they filmed me at the 5th International Marine Debris Conference in Honolulu, and then sent me a copy of their finished product after they'd gone back and done some research in Korea. And I was blown away by this documentary and asked them for permission to use the footage. And here is a Korean beach. And the fishery is shown here. It's not a pelagic fishery. It's not like nets being draped out of a boat outside the coastal zone. This is a coastal mariculture industry. We've depleted wild stocks, as you all know. We've harvested the ocean industrially to the point where species are in decline. So in order to continue to have seafood at high levels to feed the burgeoning human population, we have to become farmers of the sea. That's known as mariculture. This mariculture industry is contributing huge amounts of trash to the ocean. Now, if we're going to be farmers of the sea, we need to have some kind of the same stewardship models that we have for farmers on land. Could you imagine if a farmer on land had the town overrun with his plastic wrap and mulch from his field, and the irrigation equipment from his field was clogging the streets? Farmers are required to have bioswales to keep their nutrients trapped on their land so they don't get into the rivers. Somehow we've got to have that same kind of stewardship mentality for the farmers of the sea. This industry is booming. I've been invited to speak at a mariculture conference in China. It's a huge conference. Every coastal nation on earth now, the Baja California where I work, all the cattle barons have started staking out tuna ranches, and they bring the tuna into these ranches to fatten them up for the sushi market in Japan. Much more lucrative. You just increase the fat content 10% in a tuna, it increases the value 100%. It's fatty tuna that's in demand in the sushi market. You can get that by feeding a bunch of sardines. So you capture these tuna, put them in these pens, and fatten them up. All this stuff is generating a huge amount of trash, and we need to have some kind of understanding. That has to be part of this dialogue, this conversation about where plastic is affecting us. This is that manitrol in action, and you're not seeing the plastic in the ocean. This is the collection bag. Here's the ocean. The ocean is still a beautiful blue ocean. You survey the ocean, look at it from the deck of the ship. You see the horizon, you see the beautiful sunsets. But when I dump that bag after trawling that Newstone trawl into a petri dish, what's got me just absolutely horrified is this is what it looks like. This is anywhere out in the Central Pacific Ocean. This is anywhere from a couple hundred miles off California to China, because the Sea of Japan is even worse than the garbage patch. This is the condition of our ocean. This is what a third of a millimeter mesh net, like the width of cheesecloth, will produce, pulling it through the ocean. You've got that tube was the mariculture also. This is the oyster spacer for spacers for the oyster farming industry in Japan. There's a little pelagic crab living on that. Tire from a toy. And the plastic industry itself is a large part of the problem. Here is a pre-production plastic pellet. This is the stuff that's melted to make all these other objects. This is the raw material of the plastic. Start looking for them, start to see a lot of them here. There's like a recycled cylindrical pellet over here. Recycled pellets are often black because they're all the colors mixed together. This is a old plastic pellet. The older they get, the more pollutants get absorbed to them, and they start turning color. There's a group started by Dr. Takata in Japan called International Pellet Watch. If you go down, I was just in Victoria, went down to the beach, found these pellets there. If I collect them, I send them to Dr. Takata in Japan. His group, International Pellet Watch, will analyze them for PCBs, DDE, legacy pollutants, and they found that they're a very good marker for pollutants around the world. They've just published a study that found the farther you get from civilization, the less pollutants you have on these objects. Although there are spikes in some of them. Some of them are, even in the gyre, are very polluted. But in general, the sorption of oily pollutants, plastics being lipophilic, we have an oil spill, we deploy booms made out of plastic that pulls the oil out of the water. You separate oil from water by using plastic. Plastic is that sponge for oil that separates oil from water. So our oily pollutants sorb up to 1 million times their level in the surrounding seawater to these plastics. They become these poison pills. They desorb when they get into whatever eats them, and they look like fish eggs. They look like food. A lot of things are eating them. So we now have ways to measure pollutants worldwide using the plastics floating around in the ocean. This is a typical day sample. This is plastic and plankton. The insect that you see here, these insects are the only seagoing insect. They're a water strider. You kind of see the little legs there called the Halobades. But mostly you're looking at plastic and a little bit of plankton. It's a totally different situation at night. This is a night sample. What's happening is in the ocean, grazing occurs in the opposite diurnal cycle than it does on land. On land, animals graze during the daytime. But in the ocean, the animals graze at night. That's because during the daytime, they're subject to predation. The light makes them visible. So the small fish get eaten by the bigger fish. The small plankton get eaten by the small fish. So there's this deal migration, they call it. It's a daily migration. It's the largest daily migration of life on Earth from what they call the photic zone, from below where light penetrates into the ocean. This is where all these organisms are hiding so they don't get eaten. As soon as that sun sets, these smaller organisms come to the surface to graze on this primary productivity, the photosynthetic activity, the energy of the sun's produced during the day. So it's almost as if the field was grazed completely down to nothing every day. That's what's happening in the ocean. The small amount of productivity in these oceanic deserts, these gyres, is completely gobbled up at night by these creatures. And most of them are myctophids in terms of the fish out there. They're the lanternfish. That's the ones on the bottom in this dish. And they are called lanternfish because they have these little lanterns on them. The photophores there, you can see along the belly of the fish, is why they have their name lanternfish. They have a glowing orange eye we can see on the surface. And I've dove with these guys. They're not, leisurely feeding. They've got a window of time where they can eat. And it's dark. The reason they're the most successful fish in the ocean. A tiny little fish as big as your middle finger is 55% of fish biomass. The genus Myctophidae weighs more than all the other fish in the ocean put together, which is an amazing statistic, but not when you realize that we know so little about this huge habitat of the vast deep ocean. The habitat, which is average depth of 2 miles. You've got to swim a mile down to get halfway to the bottom. This habitat is huge. It has more living space. A mile up in the air, there's very few things living, but a mile down in the ocean, there's a lot of life. So this is a big biological habitat. It's inhabited by these myctophids. These myctophids are living in darkness. They're frantically feeding on the surface. They're not discriminating very much. What they've come up to do is feed on these, amphipods, these copepods, these little zooplankton, which have grazed on these tiny phytoplankton, these plant plankton. So the phytoplankton are the plants, the zooplankton are the next stage up, the animal plankton. Then these fish graze on the zooplankton. Well, now that zooplankton mix is plasticized, and our necropsies are finding plastic in the stomach of these fish. This necropsy done by Christiana Borger has the stomach slit open and there's a little piece of plastic in it. We're starting to find larger pieces of plastic because the mouth of the fish is bigger than the anus, and plastic doesn't get digested. That piece broke when we took it out, but it was so big that it would never have made it through the digestive system in this fish. It would have blocked it. We're starting to find the same quantity of plastic as natural food in these fish. This is one of those pre-production resin pellets here, the nurdles right here. And in some cases, there's more plastic than plankton. There's more of our trash inside the most numerous fish in the ocean than there is natural food. As I mentioned, these particles absorb pollutants from the surrounding seawater and stick there and then desorb into the animal that eats them. So not only are we feeding them non-nutritive, poisonous food, we're putting flotation devices in this fish so that when it wants to engage in that deal migration and go back down below the photic zone, its lack of energy, because we haven't fed it well, is coupled with the fact that it's got to overcome this floating, this pushing back of these floating plastics. So it's got this buoyancy it's got to fight against. Have you ever tried to dive in a swimming pool with a life jacket on? I mean, that's the kind of thing we're doing here. We're making this fish work a lot harder to get down, giving it less energy to perform that work. That's bound to reduce the fitness of the most common fish in the ocean that's feeding all the other fish. It's feeding the dolphins, it's feeding the whales, it's feeding the sea lions, it's feeding the porpoises, it's feeding the birds, it's feeding the swordfish, the tunas. The salmon eat a lot of myctophids when they're out in the ocean. If we crash this species with our trash, we're looking at major effects on the entire ocean food web. But science hasn't recognized this yet. That's what I'm saying. The plastic conversation hasn't caught up with the reality. I know it's kind of a stretch to say, well, plastic is a predator and plastic is prey, so it should be included in a food web diagram, like who's eating who in the ocean, because it's not a living substance. It doesn't fit, but it's occupying the same niche as if it were alive. It's predating on numerous species by tangling them up, making it so they can't feed. It's acting as prey because it's being consumed by all these different species. It needs to be taken into account. Science has a lot of problems when it's confronted with this kind of novelty, bringing it into the discussion. We've got to break this conceptual barrier and get this new compound into the discussion of the relationships of food and predation in the ocean. Just to emphasize this, I want to give an anecdotal report from Dr. Marcus Erickson about a rainbow runner he got to know very well on his trip aboard the junk. A rainbow runner is a jack, member of the jack family, related to the mahi-mahi. You can find it on the menus in the restaurants in Hawaii. They built a raft out of plastic bottles to emphasize the importance of getting this plastic conversation started and understanding what's happening to our ocean with this plastic trash. They made it out of 2 pontoons of derelict fishing nets filled with 15,000 plastic bottles. They made the deck out of broken sailboat masts that they lashed to these pontoons. They went out in the desert and got a fuselage of a Cessna airplane because it was waterproof and they could live inside that. They made a sail for it, although it hardly made them sail any faster, and arrived in Diamond Head there 3 months later, 3,000-mile voyage. Well, at the beginning of this voyage, going as slow as they did, they averaged about 1.5 knots. There was a lot of time to just look over the side of this boat, and they're looking down in the water and they're seeing baby rainbow runners with the egg sac still on them, obviously just hatched. So near the end of the trip, one of these rainbow runner had matured to the point where it was eaten size, and they were starting to get pretty hungry. It had become the alpha male. It was chasing all the other rainbow runners back whenever they would come out in front. It wanted first chance at whatever food was floating by. They caught that fish, brought it on board, and that was what was in the stomach of it. They decided not to eat it, knowing that these pollutants desorb from the fish, from the plastic into the tissue of the fish. So they foregoed a nice meal of rainbow runner because they found this incredible load of plastic. And their voyage took them not directly through the garbage patch, but down by the coast of Baja California, out south of the major garbage patch. So even outside this so-called garbage patch, a game fish that's well known to fish lovers in Hawaii is impacted highly with polluted plastic waste. Now, we're getting a lot more polluted plastic from the tsunami. The tsunami is like ground up a city, like put a city through a shredder and put it out in the ocean, all the plastic, wood, metal, everything. And, you know, there's a close-up of it. Anybody want to take a guess at what the first object here was that hit the coast of Washington and British Columbia? You mean you want me to tell you? It was this. This is the first object. See, the current is dragging the debris. The wind is blowing the debris. So the combination of the drag from the current, the push from the wind, the object that has the least friction on the surface of the ocean, but the highest sail, the highest wind exposure is going to get here first. And these black buoys have, they don't get waterlogged, they have high wind exposure, and they skid right across the surface of the ocean in a blow. So they're the first ones to get here. The styrofoam buoys get waterlogged, and they take longer because the polystyrene that's been expanded to make foam cracks, and these crevices where there was air become clogged with water, and so they have a little more drag, so they won't get here as fast. Now we can look at this movement here in this diagram by James Ingram Jr., this QuickTime video. And it's estimated by Dr. Maximenko that 95% of this 25 to 30 tons of 30 million tons, 25 to 30 million tons of trash will be retained by the convergent zone. But still, you know, 5% of 30 million tons is a lot of stuff, and it will impact shorelines. The first impact zone will be the Northwest Hawaiian Islands chain, where those ghost nets are removed. This is the trajectory estimated by Maximenko going toward the U.S. and Canada. And he's suggested that if we were going to do some kind of a blockade to try to get some of this stuff out, it should be at the points he's indicated with those blue geometric shapes to intercept debris before it hits BC and Washington and before it hits Curie Atoll. But this is just a scientist's fantasy, a wish. We don't have any political will to do any kind of cleanup of solid waste. That's because we've got our priorities mixed up, according to Dr. Ebbesmeyer. On a scale of 1 to 10, an oil spill should be a 3, and a plastic spill should be a 9. And the reason he says that is the solid phase of petroleum, the plastic polymer, will be causing these predatory deaths and fooling creatures into eating it for centuries, collecting pollutants, transmitting them through the food web, whereas a liquid petroleum spill will be biodegraded in a matter of decades. If that tsunami had occurred in Kuwait and hundreds of giant oil tanks had ruptured and spilled oil into the Gulf, there would have been an international response in a heartbeat. They'd have been over there with booms and they'd have been gathering that oil up and collecting it. But when that tsunami hit, since it wasn't liquid petroleum, there was no contingency fund, there was no response. That hierarchy needs to be inverted. The oil spill industry has a response that includes where you can't put your finger on the culprit. Yeah, the Exxon Valdez, we can bill Exxon for the cleanup. The Deepwater Horizon, we can bill BP for the cleanup. But if all of a sudden there's an oil slick appearing off of the Mississippi River, there's still going to be a response because they put some money away in that oil spill response fund so they can do this non-point source pollution cleanup. This is non-point source pollution, the pollution of the ocean with our waste. It needs to have the makers of that non-point source pollution, the producers of the plastics, the producers of the packaging, the retailers. These folks all need to have a fund that responds to not only tsunamis, but the daily tsunami of debris coming out of the mouths of urban rivers. The mouths of urban rivers are spewing the equivalent of a tsunami of persistent plastic trash that's going to probably kill more animals per year than climate change. And we need to have some kind of a response for that. We're going to be going out there to check on the debris on the Sea Dragon. Our foundation has a couple of slots left for scientists that want to pay to go out there and do an experiment. We'll be leaving in June from Japan to go to the debris front. We're concerned about, the habitat there at Kure Atoll, where Cynthia Vanderlip and her daughter are like stewards of that island for the Hawaii Department of Land and Natural Resources. They clean up this, that when I talk about 52 tons of derelict fishing gear, like there's a ton of derelict fishing gear in their boat here that they've cleaned up off the reef there. And their headgear is what we want to talk about right now. That's the most common beach cleanup item in a Hawaii beach cleanup. Where is it coming from? Well, the Korean documentary also gave us an answer to that question, and we'll see it here in this short video. It turns out that these cones are traps for, we thought they were traps for hagfish. We used to call them hagfish traps, where it's a deep water, jawless fish that you see on videos of whale skeletons that have dropped to the bottom of the ocean. You see all these slimy slime fish eating the flesh off of the whale. But these are not a deep water fishery. These are a shallow water eel fishery in Korea. That's what these cones are coming from in enormous quantities. And the cartoon here will show you how they're deployed. The Korean documentary crew did a cute video of that, and they show the vessel deploying these traps. And when they, the nipple there, that it's just got a string wrapped around it, I can see why they would lose a lot of them, because it's not really a very secure tie that's tied to the end of it. So the ones that eventually come to the surface are the ones we're finding over in Hawaii. And there you can see the traps. This is what a beach cleanup produces over in Hawaii. This pile over here, that's all these eel traps right there. These are all the oyster spacers that I showed in that slide of the debris from our net, from the oyster fishery. So aquaculture has a big problem we need to deal with. This is where President Obama takes his family for vacation, Christmas vacation. He was in a house right behind the beach here at Kailua where I took this picture. This is his beach turning to plastic sand. This is the plastic sand right here. This is from a Hawaiian beach. I'm going to pass it around. So the new sand has consequences. It's filling up this beach in Hawaii, Kamilo Beach, the southernmost beach. It used to have logs from here washing up there that Hawaiian chiefs would use to make their canoes with. Now it's got Coke and Tonka trucks washing up there. So turning the sand to plastic has a consequence. When sea turtles lay their eggs, Dr. Carson's found that the temperature of the sand decreases as the plastic is mixed into it. The sex of turtles is determined after the egg is laid by the temperature of the sand. If we reduce the temperature of the sand by turning it into plastic, we get more male sea turtles and less females. Not good for that species. They do cleanups there. The Hawaii Wildlife Fund has gotten funding from NOAA to clean the beach up. But the first wave after the cleanup brings in more trash. This is a beachcomber's haul before the beach cleanup on August 18th. They do these beach cleanups every 3 months. 3 months later, that same beachcomber gets the exact same haul. So beach cleanups are great, but they don't attack the cause of the problem. They keep the stuff that's on the beach from turning to plastic sand or getting back in the ocean, but they're not dealing with the cause of the problem. It's turning the beaches of Oregon. That stuff I'm passing around is not just in Hawaii anymore. It's on the beaches in Cape Blanca, Oregon. You know, it's starting to affect the northwest shoreline. There are 5 of these gyres in the world ocean. They all have plastic pollution. We've been to all 5 of them. Anna and Marcus, my colleagues, have started the 5 Gyres Institute. They've now sampled all of them. You see the myctophids in plastic. You see these windrows of plastic in the North Atlantic. South Atlantic, plastic and myctophids. Indian Ocean, more plastic. North Pacific, more plastic. South Pacific, plastic and myctophids. So when I'm worried about these myctophids eating all this plastic, I'm not just worried about the Northeast Pacific and the garbage patch there. I'm worried about the entire subtropical ocean, which comprises 40% of the world ocean. That's the equivalent to the land area of the entire world. It's a huge area that's being impacted by our trash. And the Mediterranean doesn't have to have a gyre. It's only got the mouth here at the Straits of Gibraltar, so everything going in there ends up staying there. My colleague Dr. Galgani that spoke with me at the European Commission has done underwater photography. So far we've talked about the lighter than water plastics, but about 50% of our plastic resins are heavier than seawater. Their specific gravity is greater than the specific gravity of water, and they will sink. And you notice all these bottles don't have any bottle caps. That's because the only time the bottle is going to float at polyethylene terephthalate is Dacron polyester. It's heavier than water. The cap seals in some air, the bottle will float. When that cap comes off, that bottle is, PET is heavier than water. It's going to sink. And this is a video of the bottom of the Mediterranean is getting covered up with these plastic bottles and plastic films. Not a good thing, because the place where we sequester carbon dioxide from the atmosphere is in the pore waters of the sediments. The pore waters of the sediments of the ocean are the ultimate resting place for carbon dioxide. Well, carbon dioxide would be stopped by a barrier of plastic on the bottom of the ocean. It wouldn't be able to be sequestered in the pore water of the sediment. It would change that equilibrium of sequestration of carbon dioxide. Dr. Goldberg warned us about this in one of the first papers ever published on plastic pollution, that we don't want to coat the bottom of the ocean with an impermeable layer. It's not good for the climate. So do we really want to be drinking water out of these things? Dr. Sachs doesn't think so. They leach phthalates, antimony. Dr. Ullman over in Germany has freshwater snails that he uses to evaluate water quality. On a hunch, he took some of his control snails that are in very pure water, put them in mineral water. They made twice as many eggs as the controls. There are estrogenic, bioactive compounds leaching out of this polyethylene terephthalate into the water. We don't need to have pregnant women and young children drinking this stuff. It activates, that's in vitro on the human estrogen receptor alpha, it activates the human estrogen receptor, the water from these bottles. City of Seattle banned this stuff. They have perfectly good water. You've got perfectly good water. You don't need all this water in bottles. You need to have filling stations for these things, not bottled water. Because it's taken over the world, folks. This trash is taking over the rivers in Indonesia to where you can't even see the water. Where's the water in this tributary leading to this river? Look at this river. Recycling's not working. It's only a small fraction that these folks have a market for that they can use to sell to make a living. Recycling is not keeping up. And it's not just a first world or a third world or a developed or an undeveloped. You can see this flying into LAX, Mumbai, India, Rotterdam, Netherlands, Lagos, Nigeria, Cairo, Egypt near the pyramids, Somali pirate camp, totally inundated with plastic, and they're trying not to be near civilization. So let's just assume the entire world is emanating trash. This diagram shows the coastlines of the entire world discharging trash based on buoy data that Dr. Maximenko used to predict these 5 gyres. And this is just a slow motion diagram of what's happening every day to the world ocean. Just think of each one of these dots of coming out here as millions of pieces. We did a study of the LA and San Gabriel rivers and found 2.3 billion pieces of plastic coming out in just 3 days of sampling, weighing 30 tons. So that's just my hometown, how much we're putting into this mix. But it's happening worldwide. And this, I'm going to stop this video to save time, but it would end up showing those 5 garbage patches in red. So we get these samples, we analyze them, we separate the plastic and the plankton, and we size class them. And the question becomes, what's happening to those little particles? The 4 millimeter on the left, 2 millimeter, 3/4, half, and 1/3 of a millimeter particles. We would think, why is the smallest count always with the smallest particle? And then the types, we have the list styrofoam, because I said the styrofoam gets waterlogged and sink. Then there's the plastic pellets. The thin plastic films is the most common type that we find, so it makes sense to do some reduction of plastic bags and plastic films and plastic packaging. Then the fishing gear, we've got to control the mariculture and the fishing industries, and then the unidentifiable fragments just from consumer goods, who knows where they came from. The numbers are going up, except when it's rough. The 2 arrows that show a reduction were because the count went down. The smaller particles had been submerged into the water column by heavy winds. So we estimate 90% of the stuff is down in the mixed layer below the surface in 10 knots of wind. So in 20 knots of wind, we miss a lot of the small stuff, and the counts go down. And here's the poster child of macroplastic injection, the larger particles, and the stomach of a 4-month-old chick is as big as that biologist's stomach. That's a 4-month-old chick, so you can see why it could hold this much plastic. But that's carefully been scavenged by the parrot bird, brought back, and regurgitated into the chick, so that we're getting all these bottle caps. Seem to be the favorite food now of the albatross. And that's why I'm advocating a leash law to keep bottle caps on the bottle, like we keep the pop top of a beer can on the can. We should have that same kind of technology that keeps the bottle cap on the bottle. It's just getting insane. It's affecting aquatic animals, the ring underneath the cap, in this case, and the 6-pack ring, again, affecting an aquatic species. The largest species is the eastern Pacific gray whale that's now eating the plastic on the bottom. Those bottles that I showed you in the Mediterranean are going to start showing up in these whales. This washed up on a West Seattle beach in 2010 with 20 plastic bags, small towels, duct tape, surgical gloves, pair of sweatpants. This is all stuff that's heavier than water. Are we going to have to put the gray whale back on the endangered species list after just getting it delisted because of our trash? Where are those little things going? We know that little things make a big difference in pollution. The smaller particles have a greater surface area to weight ratio and have more pollutants to transfer into the food web. This shows the way that styrofoam breaks off in the oyster mariculture industry in Korea. This is an example of another mariculture industry that's really polluting the environment with microplastics. The strand line we call the rack line, where the last wave of the high tide leaves the detritus on the beach and the sand fleas live and the birds peck, is now half plastic in that beach in Korea. And just look at the scale of this industry. It's just enormous. As I say, because we've depleted the natural stocks, the wild stocks, we're growing at an exponential rate the farming of the sea with no rational regulation of its runoff. What we call runoff in a terrestrial farm, but we need another term for it in mariculture. But just look at the scale in this fjord in Korea, how much of this styrofoam is deployed there. It's just incredible. And there's no cover on it. It just breaks off. These little bits break off and get into the entire marine food web. Look at the scale of this stuff. Absolutely amazing. So we're finding it in the salps, these chordate jellies that don't discriminate. They just pulse. Half the water column they inhabit every day goes through their bodies, and whatever sticks, sticks. And they're consuming plastic. Turtles live in these gyres because there's low predation. They don't have a lot of predators out there. And a tiny little piece, 3 millimeters in diameter, will block its pylorus and kill it. These sea urchins, we're getting this rocky intertidal habitat out there now. A sea urchin can eat a piece of plastic and spit it out, but when it gets to a tiny molecular size class, it's going to take it into its tissue. This is a Velella by-the-wind sailor that has a sticky deck. Just bumping into the plastic makes it grow a tissue over it, like a pearl oyster is irritated by a grain of sand and makes a pearl. This Velella was irritated by a piece of plastic and grew tissue over it. So we're turning actual jellyfish to plastic. We're turning the creatures to plastic without their having to do anything. I told you about getting 2.3 billion pieces of plastic. We sampled the rivers in LA, got the plastic out in heavy rain conditions and light rain and dry conditions, and 2.3 billion pieces weighing 30 tons, and most of it less than 4.75 millimeters in diameter. 5 millimeters is the cutoff for trash. When you have a regulatory system, they define trash as debris of human origin that won't pass through a 5 millimeter screen, so they ignore 90% of the trash. So let's talk about ourselves to wind this up. If it's on you, it's in you. We're living in plastic. We're wrapping plastic around ourselves. What plastics do we want to do that with? Because we used to think only high levels matter, but these conceptual shifts in science now have led us to believe that the law of Paracelsus no longer applies. The dose doesn't make the poison, it's the timing that makes the poison. That's what really counts, is when that window of opportunity is open. A vanishingly small amount can affect the developing fetus in the parts per trillion range. So why are we coating the canned food? Even the organic peas at the health food store are going to have this epoxy liner that leaches bisphenol A. A study recently completed at Harvard, they used student guinea pigs, they fed them canned soup, their bisphenol A levels skyrocketed, they took away the canned soup, and their levels came back down. Canada has already designated bisphenol A as a toxic substance. It causes hyperinsulinemia in insulin-resistant adult mice. You get this phenomena where two mice in the same diet and exercise, one will become obese and the other will be normal. It's in our serum. We have this toxic brew of chemicals, this body burden of chemicals that didn't exist before 1950, now in all of us. Anyone who gets their serum tested, you'll find this incredible brew of toxic chemicals, and no one is telling us what that synergy of all these chemicals working on us produces. Dr. von Saal believes the global obesity and diabetes epidemic is partially related to increase in man-made chemicals over the last 2 decades. It's just that third part of the equation, the diet, the exercise, but also the body burden of these estrogenic mimics. We're getting women out of girls becoming women at younger and younger ages, breast development occurring at younger and younger ages. There's behavioral consequences to this. Dr. Palaplanza in Italy found that her lab rats lost the maternal instinct if they were given BPA. They spent less time retrieving their babies to the nest, less time nursing. The green triangles are exposure to BPA, more time out of the nest. I just finished reading Realm of Hungry Ghosts by Gabor Mate. Professor Pranskep is quoted there as saying it would be disastrous if mothers lost their ability to feel intense gratification from nurturance when children were still quite young. This is this oxytocin chemical. A field of research might be to see what effect BPA and some of these synthetics in plastic are having on oxytocin production. It's in all the seafood in Singapore. A study was done, every single piece of seafood in Singapore had BPA in it. What are these kids getting? I mean, it's starting to clog up every single river. It shouldn't be our legacy, but it is. So the time has come to attack the problem of plastics in our ocean and plastics in our bodies and plastics in our lives that don't belong there. So I'm hoping that I'm able to inspire you to start that conversation. I'm hoping you'll check out further details in the book Plastic Ocean, and I want to thank you for inviting me here today to speak to you. And if you have some questions, if we have time, I don't know.
Yeah, we definitely have time. So thanks so much for that really engaging and inspiring talk. And we have the room for until about 10 to 2, so we have lots of time for questions. So if you have any questions, yeah?
First, thanks for your talk. It was really fascinating. I was interested if you have any sense of what percentage of plastics winds up in landfills on land versus winds up in the ocean.
No.
Yeah, June.
You talked about political will, so according to you, if you had political will, how would you see the next 10 years go?
Well, there's an inevitable trajectory towards greater local control and greater self-determination in the local sphere. It's inevitable for a number of different reasons, not the least of which is, running out of oil. We're going to, I'm just reading that about the end of the barista economy, we're just not going to be able to have everything imported and everything done for us, and we're going to have to start doing stuff for ourselves. People are going to, what I've done is started farming in my local community, creating an urban farm and producing my own food. You don't have to package it in plastic. 55% of fast-track trash is packaging, okay? Packaging is needed to create a moisture barrier and a vapor barrier so that goods made far away get to the citadel of consumption in a pristine condition. And when the purchaser buys them and spends that extra time getting through the blister pack and getting cut up trying to pull that thing apart and getting frustrated, he gets finally the object, if he hasn't broken it, trying to get it out in absolutely pristine condition the way it left the factory. But if the factory is next door, you don't have to do that. You can just bring it over and sell it. The guy you can go get it down the block. So we can start having food, shelter, clothing, and energy made down the block. It's going to happen anyway because we're going to run out of the cheapest way to move stuff is on a boat. Boats use the thickest you could just about take the tar sands and stick it in a boat and burn it. You don't have to do a heck of a lot to it for fuel for a tanker, and that's going to run out. My friend Jan Lundberg writes the Culture Chain newsletter. He started the sail transport network. He believes that the way we're going to get our coffee pretty soon is by sailboats running the old trade routes. So He started an international organization to bring back the age of sail. So there's a lot of movement towards localism. And so I think that's important because of the lack of packaging, because I can identify packaging in my samples as the single most common type of plastic out there that we can identify. So if we can eliminate packaging, we can eliminate a lot of the plastic plague in the ocean, and the way to do that is make the goods locally. So that would be my thought, is just continue to push what's going to happen anyway, which is the return of the local economy, you know. Yeah.
Yeah, a similar question to that. How do you envision a cleanup drive happening if that was even possible?
Well, you have to read the book to see why it's, maybe I'll read the book. How about that? I even know what page it's on. Page 309, man. You got to check out page 309. So let's look at cleaning up the gyres with no commercial motive. I mean, I'll skip the paragraph that says it doesn't pencil out to go out there and try to make a factory that, you know, runs itself on the trash, okay? So let's look at cleaning up the gyres with no commercial motive. We now know all are similarly polluted with plastic trash at concentrations like the eastern garbage patch near their ill-defined shifting centers, and that the plastics thin out toward the edges. But since the amounts are increasing rapidly, let's assume for the sake of argument that they are homogeneous at 10 kilos per square kilometer, which is, you know, a generous amount. Remember, land-based plastics are on ocean current highways to these gyres, and the highways run outside the convergence zones. Nevertheless, for the cleanup, we start with the 145 million square kilometers that comprise the subtropical gyres. And to be generous, let's say an advanced cleanup vessel can do 5 square kilometers per day with a 10-meter wide net traveling at 20 kilometers per hour, wider and faster than anything in use today. It will only take that vessel 29 million days or 79,000 years to do the job. Or for grant writing purposes, you know, you write a really good grant, you can get 1,000 boats. It'll only take you 79 years working 24/7. Now this is surface debris only, and we don't take into account the associated organisms that would be destroyed. A boat with this capability would cost thousands of dollars a day to operate. Moreover, new research presented at the recent 5th International Marine Debris Conference in Honolulu suggests that 90% of plastic debris was located below the surface layer, mixed into the water column when the wind blows at only 10 knots. So, cleanup needs to start closest to the source as possible. If you really want to do ocean cleanup, do it at the mouths of urban rivers. That's where you really need to work. That's where you can deploy your scavenger boat and get the stuff up and put it in the pyrolysis plant and heat it in the absence of oxygen and make crude oil out of it and hydrogenate it and get a truck to come in and take it to the refinery. The refinery guys love it. There are plenty of recyclers now that actually have a truck coming in once every so often, and they'll take their heated, melted plastic that's turned into crude oil, and they'll pick it up and take it to the refinery because they love it because it's equivalent to low sulfur crude oil. But you've wasted all the energy that went into the original production of the plastic item. You've just returned to the petroleum source. You get the energy that you would get from the petroleum, or a high percentage of the energy you'd get from the petroleum itself out of the object, but not the energy that went into production of the object. So you lose that. Yeah?
I understand how marine debris from fisheries and from the tsunami and disasters like that get into our oceans, but I don't understand how a Ziploc bag, plastic bottles, so much plastic ends up in our oceans. Is that just people littering, or is
well, you're a college student. That's your problem. Yeah. You got to go down to where Gabor Mate works on the east side and see how many of those folks are looking for the recycling bin, It's a pain in the ass. I mean, you go to the fast food restaurant, I'm pushing car manufacturers to get trash compactors, but the typical car has no place to put trash. And you have a pizza and some burgers, and pretty soon you got a pile this high. People just open the door and leave. I've seen piles just on the street. In LA, where I'm from, the Caltrans that cleans up the freeways says they have to do twice as much sweeping on streets that have off-ramps and on-ramps to the freeway, because people get their cars filled up with crap, they pull off the off-ramp, dump it out, and pull back on the on-ramp. There's just too much stuff, you know, and people get tired of carrying it around. It's a pain in the butt to carry all this stuff around and look for a proper disposal avenue. So people just chuck it, you know.
Could I ask a question? I'm curious about the plastics that sink. And so, because you've talked mostly, you alluded to the plastics in the Mediterranean on the bottom there, but is there any more data, and how much of the total plastic load in the ocean do we think is actually heavier than seawater and sink?
No, that's one of the fields I want to get into. We want to start looking at the marine canyons, because we have data now on how much is coming out of the river mouth into the ocean. That's what we studied. So what we need to do now is start looking at those marine canyons, and we've done surface work at the mouths of the rivers. Let's look at the marine canyons. We've done what we found. We did a multi-layer study where we took an epibenthic sled. That's a sled that drags over the bottom of the ocean that has a mouth, you know, maybe that far off the bottom. And in calm conditions, we found more trash hovering near the bottom than we did on the surface. Okay. So we think that if we go a little farther offshore and look in these canyons, you know, as the rivers come out, they create canyons like rivers do on land. And at those marine canyons are repositories for heavier than water stuff and sediments, and we think we'll probably find a lot of plastics there. So we want to start getting a handle on how much plastics are in these marine sediments at the mouths of urban rivers in these canyons. But we don't have that data yet. There has been some work done, I think, on the North Sea. It was very high percentage was covered in plastic. So there's some data out of Europe, but not a lot of really good stuff, you know, recent stuff. But I think that's one direction we need to go. Probably shallow sea is easier to do. Dr. Erickson invented a grab for deep water that he could send down and get a sediment sample. But deploying that on a small vessel of opportunity that doesn't have geo sensors to keep it, you know, over wherever it is the thing you're letting down, it's really, really hard to do. You know, it gets drug away by the current, you know. So he never got any samples with it. He wanted to do it on his, you know, the 5 gyres voyages. He wanted to go where the middle of the gyres were and let this thing down and get a sample below where all the trash was and see if there was more on the bottom there, because we think, I alluded to the fact that I thought that salps were eating a lot of the microplastics, but in an article on dispersion of oil droplets by breaking waves, I found that buoyant oil droplets, after they get below 20 microns, they act just like the water that they're in. There's no buoyancy factor there anymore. They just are transported along with that water slab wherever it's going to go. So it may be that some of these microplastics are just being transported in currents without being eaten by anything, just disappearing from the surface layer due to the fact that they're so small that they don't, the water acts like it's super viscous when something gets really small. So the buoyancy of a tiny little thing doesn't mean that much in that viscous environment, you know.
Yeah. What's your thoughts on starch-based and corn-based plastics instead of petroleum-based?
Yeah, I think there's a place in the future for biodegradable plastics and marine degradable plastics, but we have to be very careful that we understand that there are 2 separate ASTM standards for biodegradability, compostability, and marine degradability. The marine degradability standard is pretty much the same as the biodegradability standard in the ocean. So it's 60%. It's 60% in 6 months. Okay, the mass has to be reduced 60% in 6 months. All right, so there is a marine degradable plastic, and it's not PLA. PLA is what your Sun Chips bag is, you know, that has the new degradable kind of composite corn chip by Frito-Lay. that's a PLA bag. That requires a thermophilic compost of about 140 degrees Fahrenheit, and a lot of fungus, bacteria, and insects in a very dense pile that will compost it. And I've composted it at home, and the good thing about Frito-Lay and the Sun Chips bag is they give you websites to go to learn how to compost and tell you how to compost their bag. I'm okay with that. But just remember, it's not marine degradable. It's going to be about a 1,000-year product in the ocean. The bacteria are so spread out and the water is so cold that you don't get this degradation like you do in your compost pile. So metabolics with their PHA, the polyhydroxyalkanoate, we've done work for the Army. They want to start using this in the Navy because they want to be able to throw stuff overboard and leave stuff in the field. And they want to know that it's going to biodegrade. So they had us test in marine sediments and marine water this PHA plastic, and it worked. It made it through the test in a reasonable amount of time.
Petroleum-based though?
No, it's Archer Daniels Midland corn syrup, with the organism that they feed this sugar and get it proliferating in the vat, and then they gradually withdraw nutrients, and it has a stress reaction that puts on this PHA, and that's what they harvest, is this kind of stored energy that plants and animals make when they're under stress. That's the water resistant, and it acts fine except when it's in the presence of bacteria. So you wouldn't package yogurt in it, but you could package Coke in it or something like that, So yeah, there is a place for it, but you just have marine degradable doesn't marine disposable. We don't need any more nutrients in the ocean. The ocean's already overloaded with our runoff and our treated sewage. We need to keep all our nutrients on land. That's where we need it to grow our crops. So just because if we accidentally lose it, it'll degrade in the ocean, doesn't mean we want to just have, imagine a society in which we still have this runaway, throwaway mentality where everything's just thrown down on the gutter, but it starts biodegrading and clogs everything up. That could be even worse than a non-degradable plastic, clogging all the screens and all the filters and everything. All right, well, if anybody would like to get a book, I'll be happy to answer more questions. And we take $30 Canadian, and it's a cash or check. And it helps support the research because it's been really hard getting funding for this work. We have no big foundations supporting this work at all. We just get small individual donations. I have one big grant to do the river study from the state of California, but other than that, we've gotten no government funding. So it's a brand new topic. It's urgently in need of further work, but we have to kind of self-fund. So
Charles told me someone left the internet on his boat when on one of their expeditions, and it cost them 10 grand in internet fees. So they need the money.
Yeah, that's right. Yeah, you got satellite phone cuts both ways.
All right, well, thank you again for a wonderful talk.
Okay, all right.
And if anyone would like to come down and get a book or look at some of the plastics, please.
Yeah.
Okay, thank you.
All right.